So we spoke about nonlinear relationships, and we said that just like with a linear relationship where we have our data, the x and y, or x and f of x, the function of x, we also have those parameters that we need to determine. So for the linear relationship, that was the slope and the intercept. For other types of relationships, they're different. So in the case of the bell curve, the Gaussian curve or Lorentzian curve, y is a function of x, which is mediated by a, b, and c. So these are the parameters I need to estimate so that I know what the shape of this relationship looks like. And how do I go about that is a bit trickier. So with the linear relationship, we had the relationship forcibly going through the mean, and then using least sum of squares to establish where to. So we start from a point, right? We start from that mean, and now we mess about with the slope and with the intercept, and we know where the line of best fit is. Now we're trying to achieve the line of best fit here as well. But we can't start from the means. We need to start from somewhere else. And this is where we give it the starting values. So in the case of a Gaussian curve, I have A, B, and C. And in that curve, A is the peak of the curve. B is where that peak occurs on the x-axis, okay, so the placement of the peak. And C is pretty much the standard deviation, how wide my curve is. So these are real parameters, and actually parameters I'm really interested in. What is the maximum photosynthetic rate? At what temperature does the maximum photosynthetic rate occur? What is the breadth of my niche? I mean, like, these are all really important parameters for me. That's what I'm trying to extract by doing all these experiments. But I need to start somewhere, and I do that by telling the curve where to start, and then from that point the software will adjust the curve so that my error is as small as possible, right? I get the least sum of squares. So this time, if I do it in R, it's instead of having, so I'm just going to call this an NL model, a nonlinear model, okay? So this is just the name of my model. And it is an NLS, so remember we had LM, linear model, for the linear regression. Now we're using a nonlinear function, a nonlinear least square function, okay? We're still trying to minimize those squared errors. Of y, same idea, as a function of, only this time I'm putting in a Lorentzian equation, okay, which is a times the exponent x is here. The colors are just to show you, you don't put it in with color. And A, B, C, but now I need to determine where to start. A is my peak. I'm going to start it at 1. It ended up being around 4. B is where that peak happens. I told it to go to 1. It ended up being around 7. And C is how wide this is. Pretty much kind of the standard deviation-y kind of idea, the width of the curve, and I said about 3, and I was pretty much right. And if I ask for those coefficients, because that's really what I'm interested in, I can ask for the coefficients of NL mod. It will tell me what A, B, and C is based on the data I put in. Okay, so here is my data, and I've fit a model to the data. Okay, so that's how it works. So with nonlinear models, we have to start off the process by manually providing a starting point for the function to start working from. So if I look at these Lorentzian curves, okay, so this is from a study I've done on mangroves and elevated CO2 and how the temperature response of photosynthesis changes with elevated CO2 levels. There's a really interesting biological and kind of actually atmospheric reason for this. It's a cool experiment. I'm not going to bore you with the details, but what we can see is as CO2 concentrations rise from what we have today, 400 to predicted future of 800, which is already like a bit of a low prediction for the end of the century, we can see that this is the rate of photosynthesis versus temperature, the leaf temperature. So X is the leaf temperature, and I have a curve that is like that optimum curve resembles a Gaussian curve, and I know it should resemble that, so I apply that to my data. And here is the model fit, and it has A, B, and C. And I'm really interested in A, which is how much photosynthesis I'm doing, B and C. And what I can see here are, there are 2 nutrient treatments here as well. Some of them grew in high nutrients, some of them in low nutrients. But on the left, on the top 2 panels, we have 400 ppm, and the bottom panels, we have 800 ppm of CO2. What I'm interested in, let's just focus on these ones, because these ones are both high nutrients and these ones are low nutrients. Let's focus just on the low nutrients. What I'm interested in with elevated CO2 is that the temperature, the comfort zone for mangroves, and actually for all plants, is shifting up. So this is really interesting to me. So what I'm looking at is what is happening to B. Okay, so B here started off where is the optimum at about 25 degrees, and we know that's where mangroves are most comfortable. They're tropical species. With elevated CO2, I'm shifting that a bit higher. I'm shifting it to 28 degrees or 29. So that was nonlinear regressions. They're not as simple. We can try to transform them to turn them into a linear relationship, or we can work with the type of models that are specific to our discipline, and you will see them because you'll read papers and you'll see what other people apply, or you just know, and or your supervisor knows, but you will need to parameterize those models. What I want to do now is come back to the linear models, but we're going to talk about another case of them, which is the multivariate regression. So this time we spoke about it earlier briefly. We have a y, okay, a response variable, and it's responding to more than one factor at a time. And I'm asking a question like, which of all these factors I fit into my model is even important? I'm asking questions like, how does each factor affect my variable? What is the slope associated with each one of those? And most importantly, I'm asking, are these factors interacting to generate a response in my variable? So models with many variables, multivariate regressions. Remember we spoke about ANOVAs, and we talked about a one-way ANOVA that was just one variable. It's exactly the same. We can do ANOVAs with more than one factor. So remember we did an ANOVA with site, and we could have done it with site and type of vegetation, and like we can add a lot of models, a lot of variables to these linear models, and ANOVA, the type of linear model. So this time I have a y that is a function of a single intercept, right? So the intercept stays just one. And this time I have x, a few different x's affecting my y, each one of them with their own slope. Okay, so what we need to, so this time we have an equation that goes on beyond a plus bx, because we have more than one x. So I'm going to give you an example of tree growth that we talked about earlier. So y is tree growth. It equals some sort of intercept. It's probably 0, because if there's no water and there's no nutrients, I have no growth. Plus some positive slope times water availability, plus some possibly positive slope times nutrient availability. In addition, there will be an interaction that we're going to come back to. Now, I just need to make sure that the things I'm measuring are not linked to each other. So I can't say y as a function of water availability times the slope plus water availability over the month times the slope. Okay, I mean, because these two are going to be related to each other, We're trying to make sure things are not varying together just because they are linked to each other. Okay, so often we'd have humidity and rainfall, or humidity and temperature, and things that are actually varying together already affecting Y. So these different x's have to be independent of each other. And of course, everything is continuous variables. Right? So here's my regression model. So I can go B1, B2, as many as I want, BP. Of course, the more factors I include, the more data I need, right? So if I have measured only 3 locations, for example, there's really not much I can say, right? If I had included 100 factors in my model, I've only really measured, I only have 3 Y's, so there's not much I can go from, with. So this would look like if we had 2 predictors. These are those 3D plots you might be used to, so light availability, water availability, and tree growth. So what we're interested in are these regression coefficients, the slopes, the beta coefficients, or B coefficients if you want. And they represent that independent contribution. If I held everything else the same, how does variation in water affect tree growth? If I held everything the same, water is the same everywhere, how does a change in nutrients affect tree growth? So I'm looking for that independent contribution of each independent variable to the prediction of the dependent variable. And I want to know 2 things. One is the nature of that contribution. How does it affect, right? This is a linear model. I can work out the slope. And also whether that slope is different to 0 or not. Because more often than not, I will have things in the model that actually turn out to be not important. So why would we want to do a multiple regression? We do it all the time. We want to know which one of the predictors we have measured affects the variable. Now it's important to note the ones you have measured. So there are things that affect the variable that you haven't included in your model. And that is a common occurrence. We want to know who are the most important ones. Which ones have the biggest slope? I mean, like, if y changes as a function of x, which x had the biggest impact on y? Which one resulted in the biggest slope? So biggest in the positive or in the negative? So we can work that out by those partial slopes, by those betas. And of course, we have a multiple regression, and all these regression models are to allow us to interpolate and extrapolate from the data that we've collected. So we can look at levels we haven't measured. We can look at between levels we have measured. How would it look like in R? So it's quite simple. This is a linear model. We had a response as a function of a predictor. Now I'm just adding another predictor. Okay, so that's quite simple. I'm going to give you an example, and we talked about tree growth. This isn't a tree, it's like some plant thing I got off the internet, okay? So I don't even know what this is. It looks like a pansy. But we have 2 treatments here. We have sun, so some of them grew in the sun. And you can see it's quite wilted because it didn't have any water. This one had water but no sun, so it's has hydration, so it's not wilted, but it actually hasn't grown much, and it's quite etiolated. You can see these white bits. It's not a happy plant. And then I have a treatment that had both sun and water, and this is what I mean by interaction. So when I had both sun and water, the plant grew best. Okay, so in this case, having the effect of sun depends on the effect water has on the plant. Okay, so the sun times water has some sort of synergistic effect on plant growth. It could also be the other way around, right? So if I gave you an example, okay, here are the different vectors. Light, remember we can use equal or just that arrow sign, is a concatenated, okay, see, open brackets, all these different levels of light. Water, all these different levels of watering. These are probably ml And these are the measured rates of plant growth. Okay, so I can plot them against each other. Plant growth as a function of water, plant growth as a function of light. And I can run a linear model. There's plant growth as a function of light plus water. This is a multiple regression, and this is plus. Okay, so remember that, plus. When I run my model, I can ask for the summary, right? And what it will tell me are these different lines. And the first one, it will tell me call, okay? What is this? And it tells me this is the linear model with this formula. Plant growth as a function of light plus water. And you always look at this row to make sure this is really what you meant, right? It's telling me all sorts of things about the residuals. I'm sure it's interesting. I don't care. And then it gives me the coefficients. This is where I wake up, right? And it says to me there's an intercept at 3.3, which means when light and water are 0, the growth of the plant is 3.3 something centimeters per year. The standard error around that, the t-value, all I know is this is not significant because it's larger than 0.05, which means this intercept is no different to 0, okay? So there is no growth when there is no water. I mean, like, I can't confidently say there has been any growth without water or light. And then I have two factors that are influencing growth. I have light, which has a negative slight slope, and I have water, which has a slight positive slope of 0.04. Is this slope different to 0? No, it's 0.68. It's really not different to 0. This slope, on the other hand, is different to 0. So what I can say is that water has a significant effect on plant growth. Light doesn't. Okay, so in my model of how does a plant grow, all I need to do is include water. Now, down here comes something interesting. Remember we spoke about the R squared? We have R squared given to us at the bottom. And this is what's called the adjusted R squared. The adjusted R squared is the R squared we look at when we have more than one factor in the model. So if we have anything that is y as a function of more than 1x, look at the adjusted R squared. And it's adjusted for just having more information in the model. So it's, what it's doing now is it's telling me that the model explains about 45% of the variation in the data. Everything else is just that noise we can't explain. Okay, so it's not a great model. There are a few reasons why an adjusted R squared would be so low, and one of them is that perhaps I haven't measured anything of value. I haven't. I mean, like, it could be that water and light are just not important for plants. We know that's not the case. It could be that I'm missing something, maybe nutrients, maybe there were other things that I didn't take into account into the model. Or it could be that plant growth is just so valuable, it's really hard to capture. So I have an adjusted R squared that's quite low. It could be that I don't have enough points. I don't have enough samples. I want to know if this R squared is, and what I have here, hold on, is first of all the R squared. So this is a not so great model. I'd like my R squared to be much higher. I want to explain more of the variation in the data. And I can do that. I mean, like, I'm really comfortable if it's like 0.7 and up. But there is not, this is like a rule of thumb. It's not a necessity. What I am interested in is that there's a significant slope and there's a significant model. So this model is explaining the variation in plant growth better than there has been no effect. Okay, so the p-value is significant. So this is a significant model. I mean, like, it is explaining the variation. It's not random. There is a variation that is explained by the model, 45% of that variation. But there's a lot of noise. So if I fit a line, there'll be a lot of noise around the line. Okay, so this is a bit of a summary. R squared explains the variance. How good is the model? And adjusted is what we're interested in, is the modified version of r squared, and it kind of it will increase if new terms improve the model more than would be expected by chance, okay? And it decreases when a predictor improves the model by less than expected by chance. So here is multiple r squared is 0.54, the adjusted r squared is 0.44, and this is because when we added light, we actually don't need that. It's reducing our power. You know, you can see it's not a significant slope. We need to take it out. So here are my linear regression. Y is a function of the slope of light, so the B for light, the coefficient for light, times the light level, plus the coefficient for water times water level. We know now this is not important. I can take that out. Y is a function of this with a very low r squared. This could be because the relationship, and that's why it's important to plot it, it could be that the relationship is not linear by nature. Okay, so if I look at water, I see there's a lot of noise around here. Here it goes up, then it goes down, then it goes up. So it's not a good linear relationship. I'm going to explain now. Remember, we looked at the plant and we saw that there is an interaction when I add light and water. So if I have, so previously we looked at something quite simplified, but really if I have more than one factor affecting y, I need to check whether the interaction is significant or not before I do anything. So usually I would actually start here. I just started with the other way so that it's easier to follow. Can you see that instead of a plus I have an asterisk here, like a multiplication sign? And what this means is I'm going to look at plant growth as a function of light, as a function of water, and as a function of the combination of light and water. And when I look at it now, you'll see the p-values are slightly different, the slopes are slightly different. It's a different model because I've included an interaction term. But what I can see is that light and water together are having a significant impact. Okay? And when I include both of them in the model, r squared has increased. Okay? Even though I can take light out on its own, I can't remove light because light affects how the plant responds to water. So probably what's happening is if I give light but no water, you know what I mean? It's there's an interaction there. So if I apply water but don't give light, or give light and don't give water, then the plant won't grow as much, right? So this is what the nature of the relationship is. So what the true model should be is plant growth equals the intercept, okay, which is 0.27, I should have rounded, no, 0.26, plus the slope for light, 0.433, plus slope for water times water, plus water times light times the slope of that interaction. So when should you include an interaction term? If it is significant, you keep it in and you run a model and you write it out like that. If this does not come out significant, simplify your model, run it again with a plus. Okay, so run the model again without the interaction. So that's called simplifying the model. And you keep simplifying the model by removing things that are not significant. Right? So there are some, so this is a great tool, and I'm sure you can see the value of it, but there are limits that we need to take into account. One is, we're good at patterns, and we're good at putting things, so this person had this cloud of data, and you can put a line through it, right, and it will have a slope that's not, 0, but look at this r squared. At 0.06, it's so low. So if it's really hard to guess what's going on here, and actually you could fit something like that just as easily, then don't put a line in. Okay, don't trust this linear regression. Limits and so of course there's limits to, don't put a line everywhere. If r squared is so low, there is no significant model here. So it's okay to just leave it as a cloud. But even if you do have a model, you have to be really careful. Remember, with causation, we don't know the direction of the cause. Does x cause y? Is y causing x? You need to, there could be another variable that's involved that is responsible for that covariance between x and y. You have to be